All right, so I will now continue with the discussion of double bracket flows, and let us consider the monotonicity equation. So for the monotonicity equation, I have to consider, for the monotonicity equation, I need to consider the Hilbert-Schmidt norm of some float observable HS. I will square it in my notation here, and I will consider the trace of the square of this observable, which is the evaluation of this Hilbert-Schmidt norm for the off-diagonal part of sigma. Just as a reminder, sigma of AL is the identity minus delta applied to AL, which means I have AL minus delta of AL. Delta is the diagonal restriction. So in the paper, I'm discussing this as also the dephasing channel. And what all this tells you is that sigma is Hermitian if A is Hermitian, right? And from this follows that then we have both conditions. Okay, so those two are Hermitian, which means that the canonical bracket is then anti-Hermitian, right? So because this is Hermitian, then I get that the Hilbert-Schmidt norm, of A is the square root of trace of A dagger A on half. So this is the square root of trace A squared for A equals A dagger. Okay, so that's the expression we want to consider, the trace of sigma AL. Now, next in the monotonicity equation, we were considering sigma of AL, Schmidt norm. So now I need to be able to take the derivative of the trace of sigma of AL squared. Okay, so in the appendix of my paper, I spend a little bit more time on checking that everything goes through. Basically you get a lot of linearity and continuity considerations that you can put in, but then in the end you realize that that actually when we consider the derivative of sigma of AL, sigma of AL using trace simplicity already here, then this is 2 times trace of sigma of derivative of AL, and that's very nice because the derivative with respect to the flow duration of the float observable satisfies the double bracket flow equation. So the double bracket flow equation is W, I will write subscript L, I L, close here, sigma AL here. where W is just the bracket that we use for the flow. So now I switch to the notation from the paper, which is canonical bracket of AL, which is a bracket, delta diagonal restriction of the float observable A, sigma of diagonal restriction of AL, and close the bracket. All right, so next what we will do is to consider what happens if I expand. So I have 2 times trace of sigma of bracket L AL, close the bracket, and then I will have AL and minus, I have already scribbled minus here, trace sigma of the right hand side of the double bracket flow equation, AL here, close here, correct, and then I have a delta of AL here. Okay, I switch to color, and there are 2 comments. This term, together with the trace, I will refer to this trace induced cyclicity. Actually, I did it incorrectly, because this will not work like this. I have to expand the definition of sigma for this one, and this one keep. Okay. But anyway, when we will do this trace-induced inequality, it will be one term that we will consider, and then here we will use Hilbert-Schmidt orthogonality. So that will be 2 relations that we will need. Okay, let me do a couple of corrections. So I will have this here. I will keep this here. And in color, I'm correcting sigma. Delta applied to the double bracket. The double bracket stays, and sigma AL stays, like this. Okay, let me see if I can move it. No, that didn't go well. All right, I cannot stop it now. But yeah, there's the. It's just expanding sigma for the double bracket. Okay. So let's consider this trace of delta A, where A and B are just generic operators. What is this? This is 0. Why? Because this is strictly of diagonal. I don't even know what strictly means here, but it's like off diagonal. Off diagonal matrices have 0 trace. And this is diagonal. And the proof argument is basically sigma of A. So a diagonal matrix times off diagonal matrix is again off diagonal. So it has 0 diagonal. So then the trace evaluates to 0. So how do we check that? For example, in a basis, we can express this as A, K, 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 and sigma of A is K not equals to K prime, A, K, K prime, maybe with a bar here, k prime, k prime. If we multiply the two together, so maybe here a b and here a b as well. B k prime, sigma p is the summation k prime not equal to k bis, ak b k prime k double bar k prime k double prime, and we will see that we will get a delta k prime, and so those two will be equal. These two are not allowed to be equal because it's strictly off diagonal, so it's again in the image of sigma for some operator c. So it's off diagonal, and that means that trace sigma of some c is always equal to 0. So that's our first property, which means that, we do this in pink, this one, due to this Hilbert-Schmidt orthogonality, goes to 0. And the next property is to use the trace cyclicity. So let's see how that will work. So let me consider a new color. And I consider trace of a bracket A, B, C. And now if we consider this commutator, this trace, then I can write this as trace A, B, C minus trace B, A, C. And what I would like to get is the commutator of BC, and that's it. Okay, so let's see if that will work. Okay, so if I move it here, I will get BCA. If I move this one here, I will get CBA. So let me do that. I'm just using trace cyclicity. BCA and close here minus trace CBA, which means that I get trace commutator B with C and A. So now now this I will call trace induced cyclicity, because I used cyclicity of the trace and I got some sort of cyclicity of which operators are commuting with each other. So now on the previous page, we had, and it's easy to know what we had. So I had to drop the sigma of the double bracket flow equation. So I have here AL evolved, and here I have sigma AL because I cannot drop this one so easily. Okay, and now this is A, this is B, this is C. Okay, so now I get, by this trace induced cyclicity, I get AL comma sigma AL bracket, and then A goes outside A from the lemma, so I get this. And now a simple calculation, AL sigma AL is equals to a delta of AL plus sigma of AL, just a decomposition into the diagonal and off diagonal of any operator. Sigma AL stays here, and we see that this becomes WL. So what do we get? We get trace of WL squared. Okay. So let's let's recap. I wanted to consider the change of the magnitude of the off-diagonal restriction of the float observable A. And to do that, we take the derivative of the trace of the observable squared, okay? And then we just continue with the calculations. Yeah? So I have this one. Then it's the observable squared. So I can actually put the parentheses here for clarity. And then we just use the Leibniz rule. So we get this 2 from the Leibniz rule. I need to have the derivative, but the derivative I can take inside because that's in some way a linear transformation. So everything works here nicely. When the derivative is here, this is a solution of the double bracket flow equation. So we put it here. Then we decide to expand this by the definition that sigma is this operator minus its diagonal restriction. So this operator together, it's just what we computed is that WL will go here, and then AL with sigma of AL will be here. Now this becomes 0 because even if I take a diagonal operator, multiply it to something traceless, it remains traceless. So this one we forget, and this one we just showed that this is trace of this anti-Hermitian canonical bracket squared. And the cool bit is that this bracket is anti-Hermitian. And the definition of the Hilbert-Schmidt norm is that the Hilbert-Schmidt norm of some operator A is the square root of this. So I need to consider this, which means that if I consider the derivative sigma AL plus HS squared, then this is 2 times trace of WL not squared, but this is minus 2 times trace WL dagger WL. So this is minus 2 times the Hilbert-Schmidt norm of WL squared HS, which is this is non-negative. So together we get that this is non-positive. Hooray. I love this relation. It's very nice. So basically this anti-hermiticity that gives us the unitarity is also crucial to get this this non-decrease. All right, so a little bit of a recap maybe. Okay, so what do we have? I said that we want to consider the Hilbert-Schmidt norm just defined with this A dagger A, and this A dagger is crucial. It's not crucial for a Hermitian observable. So for example, for sigma AL, this is Hermitian. So this becomes just simply the trace of sigma AL squared, okay? And I was repeating here the definitions. Later we need that the restriction is the operator and remove the diagonal. And delta in my notation is the diagonal restriction, okay? Both operations preserve hermiticity. So now if we continue, the derivative, the change of this magnitude of the off-diagonal restriction during the flow is just simply consider this. So we use the Leibniz rule, then we need to enter with the derivative inside of the off-diagonal restriction. This can be done. And then this is a solution to the double bracket flow. And then we decide to use the definition of the off-diagonal restriction using the delta here. And this gives us 2 terms. For one, we will use the trace cyclicity. For this one, we will use that this traceless operator remains traceless even if we multiply a diagonal operator to it, and so this vanishes. I call it this Hilbert-Schmidt orthogonality here. And trace-induced cyclicity is just coming from applying the trace applying the trace in this setting of having a bracket. So the cyclicity allows me to move the operators forward, backward, and then I will see that suddenly I have the commutator here, and I multiply out A, so I get basically that I can move those operators in. So B goes here, C goes here, A goes here. So when I do it in our setting, we start with the double bracket flow equation here, or the right-hand side of the double bracket flow equation. So this becomes A, this B, and C in this notation. So suddenly sigma of AL can go inside, AL goes here, so we have it here, and the canonical bracket will go to the last position, WL. And a simple calculation shows that we can decompose AL into the diagonal and off diagonal. The off diagonal will have diagonal commute. So we are left with the canonical bracket here. So we had it here. We get another one. Suddenly we have trace WL squared, and you would think, okay, is that a problem? But it's not a problem because it's anti-Hermitian. So when we have it here, suddenly, if we want to have a form where we can identify it as the squared Hilbert-Schmidt norm, we need a dagger. So we get a really important minus sign here, which means that the whole expression is non-positive, which means that the rate, which is exactly equal to the Hilbert-Schmidt norm of the canonical bracket, that's why it's canonical. It's having this important role for this double bracket flow. So this canonical bracket is here recovered, and this becomes non-negative, which means that during the flow we are non-increasing the magnitude of the off diagonal. But if the Hilbert-Schmidt norm of the double bracket of the canonical bracket happens to be non-zero, so that operator is non-zero because norms are non-degenerate, then we have a finite rate of the decrease. So we start decreasing this off diagonal. Yeah. And how to know that you have this? It's just a question, is your operator wanting to be diagonalized? Yeah. So it could also be that it has a non-trivial off diagonal, but it commutes with the diagonal part. So then you have some symmetries in your matrix. If you have a generic matrix, this WL will be non-zero, and you will have a finite rate. It will be a strictly non-zero decrease of the off diagonal, and that's the meaning of the monotonicity relation for the GWW flow.